This module is titled Mathematical Preliminaries, Part 1. In the previous module, we were introduced to the basic approach to semantics we take in this course, as well as an introduction to notions like denotation and the like, and how one may go about building a theory of semantic composition. Before we can see examples of what a compositional theory of semantics for fragments of natural language looks like, however, we need some mathematical preliminaries. You need to know some basic concepts from mathematics and logic. In this and the next module, we will introduce some basic notions from set theory, namely sets and various operations that we define on sets, as well as relations and functions that can be defined on sets that we make use of when we see examples of semantic composition for simple fragments from natural language. So some basic concepts of set theory. Sets and elements. Set theory is a basis of modern mathematics, and the notions of set theory are used in all formal descriptions. So the notion of set is taken as undefined, primitive, or basic. So we don't try to define what a set is, but we can give an informal description, describe important properties of sets, and give examples. All other notions of mathematics can be built up based on the notion of a set. Sets often go by various other names. So you might, if you look at textbooks on set theory and so on, you might encounter words like collection, group, aggregate, and so on. For our purposes, they mean the same thing as sets. There might be some differences between different variants of set theory, where some of these might have a slightly different meaning, but for our purposes, these differences don't matter. A set is a collection of objects which are called members or elements of that set. If we have a set, we say that some objects belong or do not belong to this set. They are or are not in the set. We say also that sets consist of their elements. Examples: the set of students in a classroom. The English alphabet may be viewed as the set of letters of the English language, the set of natural numbers, etc. So sets can consist of elements of various natures: people, physical objects, numbers, signs, other sets, etc. We will use the words object or entity in a very broad way to include all these different kinds of things. A set is an abstract object. Its members do not have to be physically collected together for them to constitute a set. The membership criteria for a set must in principle be well defined and not vague. If we have a set and an object, it is possible that we do not know whether this object belongs to the set or not because of our lack of information or knowledge. For example, the set of people in this room over the age of 21, a well-defined set, but we may not know who is in it. But the answer should exist, at any rate in principle. It could be unknown, but it should not be vague. If the answer is vague for some collection, we cannot consider that collection to be a set. If we have a set, then for any two elements of it, x and y, it should not be vague whether x equals y or they are different. If they are identical, they are not actually two elements of it. The issue really arises when we have two descriptions of elements and we want to know whether those descriptions describe the same element or two different elements. For example, is the letter Q the same thing as the letter lowercase q the same thing as the letter uppercase q? Well, it depends on what set we are considering. If we take the set of the 26 letters of the English alphabet, then lowercase q and uppercase q are the same element. If we take the set of 52 uppercase and lowercase letters of the English alphabet, then lowercase q and uppercase Q are two distinct elements. Either is possible, but we have to make it clear what set we are talking about so that we know whether or not lowercase q equals uppercase Q. Sometimes we simply assume for the sake of examples that a description is not vague when perhaps for other purposes it would be vague. For example, the set of all red objects. Sets can be finite or infinite. In fact, in set theory, it is customary to define what it means for a set to be finite or infinite. This is a topic that we will come back to in the next module, which is Mathematical Preliminaries Part 2. There is exactly one set, the empty set or the null set, which has no members at all. A set with only one member is called a singleton or a singleton set. Okay? We often call this a singleton of A. So if A is the member, the singleton of A is that set which has A as its member and nothing else in it. Notation. In this module, we use uppercase A, B, C for sets, lowercase a, b, c or x, y, z for members. We say B epsilon A if B belongs to A. Okay. Or we might say uppercase B belongs to uppercase A if both A and B are sets and B is a member of A. Remember, sets can be members of other sets. We also say C epsilon with a slash in between the epsilon if C does not belong to uppercase A. The Greek letter, a variant of the Greek letter phi is used to indicate the empty set. Specification of sets. There are three main ways to specify a set. You can specify a set by listing all its members. This is called the list notation. The second way of specifying a set is by stating a property of its elements. This is called the predicate notation. A third way of specifying a set is by defining a set of rules which generates or defines its members. These are sometimes called recursive rules. List notation. The first way of specifying sets, namely the list notation, is basically suitable only for finite sets. In this case, we list the names of elements of a set, separate them by commas, and enclose them in braces. For example, if we say 1, 12, 45 in braces, that means the set whose members are 1, 12, 45, and nothing else. Or Manmohan Singh, Jawaharlal Nehru in braces, A, B, C, D, M inside braces. We might also use a 3-dot abbreviation when it's clear what the 3-dot abbreviation means. So you might see something like 1, 2, followed by 3 dots, 100, all of them enclosed in braces. This means the set of all numbers from 1 to 100. We sometimes also use something like a list notation for infinite sets. So for example, we might say 1, 2, 3, 4, comma, followed by 3 dots and have this in braces. This is not a real list notation. It is not a finite list, but it's common practice because the continuation is clear, because we know the things that are going to come afterwards are each natural number in succession. Note that we do not care about the order of elements of the list, and elements can be listed several times. So 1, 2, 45, 12, 1, 45, 45, 12, 45, 1, 12, 1, 45, 1, they are all different representations of the same set. Okay? See below the notion of identity of sets. What about the predicate or abstraction notation? Let's take the following example. Braces the set of x's such that x is a natural number and x is less than 8. This needs to be read as the set of all x's such that x is a natural number and x is less than 8. So the second part of this notation is a property of the members of the set is a property the members of the set share. This is a condition or a predicate which holds for the members of the set. Other examples: the set of x is such that x is a letter of the Devanagari alphabet. The set of y's such that y is a student of JNU and y is older than 25. The general form of the predicate or abstraction notation is the set of x's such that p of x, where p is some predicate which is a condition or a property. The language to describe these predicates is not usually fixed in a strict way, but it is known that an unrestricted language can result in paradoxes. So, for example, the set of all x's such that x is not a member of x leads to something known as the Russell's paradox. So, for example, if you take this as a set and ask whether this set is a member of itself or not, you are led to the conclusion that it's a member of this set if and only if it is not a member of the set. And that's a paradox. The moral: not everything that looks on the surface like a predicate can actually be considered a good defining condition for a set. Solutions, type theory, other solutions, we won't go into them. Okay? If you're interested, see the reference cited below. The other way of defining is by recursive rules. This is always safe. So, for example, we say that the set E of even numbers greater than 3 is defined as follows. 4 is a member of uppercase E. If x is a member of uppercase E, then x plus 2 is a member of uppercase E. We say C, nothing else belongs to uppercase E. The first rule is called the basis of recursion. The second one generates new elements from the elements defined before, and the third rule restricts the defined set to the elements generated by rules A and B. The third rule should always be there. Sometimes, in practice, it is left implicit. It is best when you are a beginner to make it implicit. Identity and cardinality. Two sets are identical if and only if they have exactly the same members. So A equals B if and only if for every x, x belongs to A if and only if x belongs to B. For example, the set described in list notation as 0, 2, 4 is the same as the set of all x's such that x is an even natural number less than 5. From the definition of identity, it follows that there exists only one empty set, because if there could be two empty sets, okay, they would have to have at least one member that's not in the other. Okay. Since they're both empty sets, they have to be the same. Okay. Its identity is fully determined by the absence of its members. Note that the empty list notation just braces is sometimes but not usually used for the empty set. We have a special symbol phi for it. The number of elements in a set A is called the cardinality of A, written A within two sticks. Okay. The cardinality of a finite set is a natural number. Infinite sets also have cardinalities, but they're not natural numbers. We will discuss cardinalities of infinite sets a little later. Subsets. A set A is a subset of a set B if and only if every element of A is also an element of B. Such a relation between sets is denoted by A is a subset, denoted A, a horseshoe with an equal sign below it, B. If A is a subset of B and A is not equal to B, we call A a proper subset of B, and we write A horseshoe B without the equal sign below. As a note of caution, sometimes the horseshoe is used in a way we are using horseshoe with an equal sign below. Both signs can be negated using a slash through the sign. So example, the set consisting of AB is a subset of the set consisting of DABE, and AB is a proper subset of DABE. AB is a subset of AB, but AB is not a proper subset of AB. Note that the empty set is a subset of every set. So phi is a subset of A for every set A. Be careful about the difference between member of and subset of. This is a common mistake people make frequently when you're first encountering set theory, is the notion of a power set. The set of all subsets of a set is called the power set of A and is denoted as pow A or Gothic P with the argument A, or sometimes as 2 to the power A. So for example, if A is the set consisting of AB, then Gothic PA is the set consisting of the empty set, the singleton of A, the singleton of B, and the set consisting of AB and nothing else by itself. Note that if the set A has a cardinality of n, the power set of A has the cardinality 2n, 2 to the power n. This can be proven by using some high school algebra using the binomial theorem. Operations on sets, unions, and intersections. Let A and B be arbitrary sets. The union of A, B, written A, U, B, is the set whose elements are just the elements of A or B or of both. In predicate notation, the definition is A union B, by definition, is the set of all x's, so that x is in A or x is in B. Here we look at a few examples. The intersection of A and B, written A upside down U, B, is the set whose elements are just the elements of both A and B. In predicate notation, the definition is A intersection B, by definition, is the set of all x's such that x is in A and x is in B. Here again, we look at a few examples of sets K and L and see what their intersections will be. Some more operations on sets. Difference and complement. Another binary operation on arbitrary sets is the difference that we call A minus B, okay, which subtracts from A all elements which are in B. This is also called the relative complement, or the complement of B relative to A. In predicate notation, the definition of this operation is defined as follows. A minus B, by definition, is the set of all x's such that x is in A and x is not in B. Example, if we use the previous sets K, L, and M, K minus L is the set consisting of AB, K minus M is the set consisting of A, L minus M is the set consisting of C, K minus K is the empty set, K minus the empty set is K, the empty set minus K is the empty set. A minus B is also called the relative complement of B relative to A. This operation is to be distinguished from the complement of A, which is often written A apostrophe, which is the set consisting of everything not in A. In predicate notation, we say A complement, by definition, is the set of all x's such that x is not in A. It is natural to ask, where do these objects come from which do not belong to A? In this case, it is presupposed that there exists a universe of discourse and all other sets are subsets of this set. The universe of discourse is conventionally denoted by the symbol U. We have A apostrophe, by definition, is U minus A. Ordered pairs and Cartesian products. The way sets are defined, they are taken to be unordered with respect to their members. Thus, the set AB equals the set BA even when A is not equal to B. This is because a set is identified purely by its members. However, for various purposes, we might want to deal with set-like objects where the order of elements matters. Such an object is an ordered pair written angled brackets A, B, okay, in which A is called the first member and B is called the second member. Such an object can be defined in terms of sets in any different ways, but here there is a common or standard way of defining, which is to say that the ordered pair AB is the set consisting of the singleton of A and the set consisting of AB. You can easily convince yourself, this requires a little bit of work, that if A is not equal to B, then AB is not equal to BA, given this definition. It also follows from this definition that if the ordered pair AB equals the ordered pair CD, then A equals C and B equals D, and vice versa. And this is a desired outcome. As an exercise, you may want to try to prove this. Now, the notion of an ordered pair can be extended to ordered triples, ordered quadruples, ordered n-tuples easily, and these can come in handy in various applications. Okay? We do this as follows. Here's what you see. Cartesian product. If A and B are sets, the Cartesian product of A and B, written A cross the multiplication sign B, is the set of all ordered pairs whose first member is a member of A and the second member is a member of B. In predicate notation, we may write the definition as follows. The Cartesian product of A and B is the set of all ordered pairs x, y, such that x is a member of A and y is a member of B. Note that the Cartesian product of A and the empty set is the empty set. As examples of Cartesian products, consider the sets K equals ABC and L equals 1, 2. Then the Cartesian product of K and L, L and K, L and L, K and K, etc. Are what you see below right here. As an aside, note that there is a strict relationship between the cardinalities of AB and the Cartesian product of A and B. It is easily verified using some high school algebra that the cardinality of the Cartesian product of A and B is simply the product of the cardinalities